I'm here representing a team of folks, not just at NC State University and the climate program there, but all of the state climatologists and the climate extension specialists across the region, many of whom are located at the land-grant institutions from Texas A&M all the way up into the Carolinas and Virginia. I'm going to talk today a little bit about the climate scenarios that we're using to look at projections of climate and the responses and opportunities and risks for the PINEMAP objectives here over the next short term as well out over the next 100 years. I'm going to start with a very brief introduction to climate models. Now, many of the folks in the room are familiar with ecosystem and physiological models. The climate models work a little differently, and they're important for us to understand those differences in terms of how we interpret the results of the output from these as they go into some of the other physiology models and market models, economic models. We're familiar with weather models. Weather models are trying to give us tomorrow's high temperature and where the rain is going to be and how much is going to fall tomorrow or the next few days. Climate models work on some of the same basic principles. They rely on physics and equations of physics to simulate the interaction between what's happening at the oceans, the land surface, as well as the atmosphere. But climate models aren't trying to tell us what the temperature is going to be and the chance of rain is going to be on August 22nd of 2062. Instead, what climate models are trying to do is look at how the weather patterns over a broad sense are likely to change. Not in necessarily August of 2062, but maybe in the summertime of the 2060s. And all of those are predicated on some sort of external forcing, some sort of change. Most of these climate models are focused on what happens when you change atmospheric chemistry, primarily through greenhouse gases. But there are other factors that change in the climate models that we try to account for. So, for example, we can do simulations where there are changes in the broad-scale land surface. So if we suddenly melt all of the ice in the Arctic, what's the response in the climate system? What happens if we suddenly cut down all of the pine trees in the southeast? That actually has an impact on the local climate. Certainly, the substantial change in climate has been observed in the southeast over the past 100 years because we've largely reforested much of the southeast. So we can take these external forcings and run them through the climate model and then see how things change. We make these assumptions, in particular here, what you see up here are 5 different assumptions of which we primarily look at 4 as to what the energy usage is going to be and what the general greenhouse gas concentrations are likely to be over the next 100 years. And so there's scenarios that are chosen. These represent 2.6, 4.5, 6, and 8.5 net increase in the radiative forcing in the climate system. And these are the same scenarios that are used by the Intergovernmental Panel on Climate Change. And that's one of the reasons why they're widely used. They take into account all kinds of different factors, but we have to break these down into different scenarios so that we can see how the resulting climate may be. And that's why they're not called climate predictions, but climate projections, because we have to assume these different scenarios in order to see how things might evolve over the next 100 years. Now, global climate models do some things very well. They capture broad-scale flow, they capture annual temperatures, they generally capture the annual temperature and precipitation cycles. As a general sense, looking at global patterns and even continental scale patterns, they do a pretty good job there. They handle a lot of the core forcings that we know that are important for longer-term climate variation, as well as even some interannual climate variation. So most climate models have something like an El Nino, which we know is very important for modulating wintertime precipitation and temperature patterns in the southeast. But each climate model does some things differently when you start getting down to regional and more local scales. And so climate models really aren't very useful when it starts trying to ask questions about what's happening locally. So the global models are very coarse. We simulate the physics of the atmosphere, every few hundred miles. We can't resolve then what's happening on the differences across complex topography. One side of the ridge versus the other side of the ridge, mountain versus valley, urban versus rural, complex coastlines. And of course, certainly the Southeast has all of those. Global climate models, because they're so coarse, aren't able to resolve things like the appropriate intensity of hurricanes, much less tornadoes or individual thunderstorms. So the global climate models really aren't designed to answer those kinds of questions and give us those kinds of projections. We shouldn't expect them to try and do that. And even with some of the broader scale differences like El Nino Southern Oscillation, which is really important for modulating our interannual variability in the climate pattern in the Southeast, all the global climate models have some sort of an El Nino-like structure, but they don't all quite agree or match very well with the timing and evolution of those. So there's still a lot of active research that certainly is going into the global climate models. Because the global climate models don't capture and answer or give us the kind of guidance we need at the scales that we need for PINEMAP, we have to go through this process called downscaling. And downscaling is simply how do you take what's happening with the global climate models and relate it to what's happening locally for the climate system dynamics that we know impact us locally on the order of, say, a county. And so we take where we go, for example, with a very coarse climate model and this sort of resolution. We might pick out an area of interest here. The example here is the coastal Carolinas, and allows us to go and look at something much more focused. So if we're interested in the temperature variations in coastal Carolina, this might be a way to downscale and get a better sense as to what the broader scale forcing in the global climate models might have an impact to local scale things that we're most interested in. Now, downscaling is really important. There's a whole separate industry of climate scientists that focus on downscaling. It's not a very large industry. There's maybe a few dozen people total that do it. But it's really interesting, and it's an active area of research because there's not a standard technique that everyone uses. And what we found is that there are a broad variety of techniques that folks use to answer some specific questions. And some techniques are more appropriate for some questions, other techniques are more appropriate for others. But in general, there are two broad types of downscaling. We have statistical methods, and we have dynamic methods. Statistical methods really establish a relationship between what the global climate model has predicted over the past and what's been observed locally. So we might have a few dozen global grid points that cover the southeastern US, but we have hundreds of local weather stations that have been observing temperature and precipitation for 100 years. So we can establish this statistical relationship between what the global model says and what happens locally. And we can do that statistical relation, that matching to the probability distributions, and allow us to downscale to local information that we can then project into the future. Dynamic models, on the other hand, basically take a regional climate model and embed it inside of a global model. It allows us to do the full physics simulations of the atmosphere and the land surface system, and allows for much more rigorous complexity in trying to answer some of the scientific questions we have about local climate variations. Now, statistical methods have some real strengths. One, it allows us to do bias correction and allow for variations that occur in the climate models that aren't well resolved. We can actually customize those and calibrate them to surface observations. We can also use appropriate statistical methods that are widely employed to answer and address specific problems. So if you want to focus on extreme events, you might use statistical methods that focus on rare and extreme events. However, some disadvantages associated with statistical models. The biggest one being that you really have to have an observed data set of that history, which is fine if you're focused just on temperature and precipitation. But let's say you're really interested in clouds. You're really interested in humidity. You're really interested in incoming radiation. The statistical models don't really do a very good job with that because you don't have that very long, robust history of observations that are so important for statistical downscaling. Dynamic models solve a lot of the issues that are created with statistical methods. You don't have to have a long history of observations to do statistical downscaling. You can resolve all the physics in the atmosphere and the land surface system. You can have every possible imaginable variable resolved. You want to know how the clouds are distributed across 4 layers in the atmosphere? No problem. But dynamical downscaling requires massive, massive, massive amounts of computing. The largest supercomputers in the world are largely used for genetic analysis, nuclear weapon simulations, and dynamic downscaling in global climate models. So we simply don't have a lot of the computing needed to do all of the downscaling that we would need using dynamic methods. Statistical methods, on the other hand, can be run on this laptop, and in a few days get a lot of the answers that you need. So we are able to do a lot with statistical methods. We're able to do a lot with dynamic methods. It really comes down to what are the needs and what are the most appropriate tools then to get at the answers that you're searching for. So some examples, some folks may be familiar with the NARCAP, the North American Climate Change Assessment Program, focusing on regional dynamic downscaling. It took them about 7 years, and they only have a handful of models. Some of these statistical methods that are over here, the bias correction, statistical disaggregation, there's a group Catherine Hayhoe put together for CRAP, and then this MACA data set that we're going to be using, and I'll talk a little bit about later. These use purely statistical methods, and in a few months you can have 20 different GCMs with a variety of different methods outscale. So it allows us to have a lot more information in a much faster time step. And it's important to think that downscaling is not just interpolation from individual points. A lot of us look at the different interpolation methods out there, whether it's a area weighted average or thin spline fits. Downscaling is not interpolation. Downscaling is trying to resolve new physics, new climate information that isn't otherwise captured in the coarse models. Interpolation is really just smoothing out what's going on between information to create a nice pretty grid. It's useful in a lot of applications, but really for what we're trying to get at, you can't just interpolate. We really have to go through a downscaling process because we're interested in changes in local variations in the climate that we know exist. We want to be able to capture those and then project them into the future. The other thing that's really interesting about models, in particular on the climate models, is with the global climate models, there's no single best model. You may hear on the evening news, your local broadcast meteorologist gets up and says, oh, the European model is really nailing this one. This is the best model, and we really use it a lot. And another one may say, well, for winter storms, we really like this GCF model over here that's going to really solve all of our problems. With global climate models, it doesn't work that way. All of the climate models do something well and something not so well. What we found is by creating an ensemble, a group of models that we can then merge together statistically, we actually get more guidance and get a sense as to what the range of uncertainty is. And it's really important for issues and priorities for PINEMAP. Using an ensemble of a wide range of models allows us to characterize where the uncertainty is, what things the models are generally doing well and which things they aren't doing well. It also allows us to actually reduce some of the internal uncertainty that we have among the spread. I'll give you an example here. So this is from the MACA downscaling output. It's just the change in minimum temperature during the wintertime, mid-century, in a 30-year period in about mid-century, as compared to our baseline period since 1950. And what you see up here are, if all the models were perfect, they would all look the same. There's a tremendous amount of differences into how the different models resolve the different projections for the future. None of these is perfectly accurate. But when we combine them together, we actually get more skill, more guidance, more useful information from the multi-model ensemble mean. And so in addition to seeing something like this that actually has more skill, more useful information, better predictability than any single model, we also allow us to characterize what the range of uncertainty is about any of those one points, any one season, any future period. So, quick recap on the climate models before I get into the details of the MACA data set that we're very excited about. We know that the global climate is going to change. It's going to have manifestations in terms of variations of local climate. The historical data that we've always used to give guidance for the future is probably going to be useful still for the next decade, maybe even the next 2 decades. Really, by mid-century and beyond, what's happened in the past is not a good reflector of necessarily what's going to happen in the future once you get that far out. We use global models to capture what happens very broadly. We have to downscale those global models to get a sense as to what's happening locally and regionally for the scale of things that are important to PINEMAP researchers and PINEMAP mission objectives. Now, MACA is, we call it MACA because no one likes saying multivariate adaptive constructed analogs. And like PINEMAP, we needed a good acronym. This is a method that's been established and published by John Abassoglu at University of Idaho. He's been playing with this a lot, focused on the Pacific Northwest for a few years now. And we had previously thought that the NARCAP dynamically downscaled projections were going to meet a lot of the needs. Well, it turns out that it's not going to meet all the needs, and we really needed a different data set. But we went off, we started surveying some of the other data sets that were out there. We talked to John Abassoglu, and he said, yeah, you know, we've been talking about maybe trying to do something. We think the methods are appropriate across the entire continental U.S., with maybe the exception of the Caribbean and South Florida, that the analogs that we choose that are representative of the Pacific Northwest in terms of the dynamic flow in the atmosphere are pretty representative everywhere. I said, great, so how fast can you do it? We'll see what we can do. So they moved forward with it. They went ahead and moved forward. And so for the past couple months, we've had downscaling model trickled in. I think the last model sets came in about 2 weeks ago. So this really is brand new stuff that even I haven't looked at all the way. You're going to see some of the example output up here in a minute. This is, in many ways, very exciting, very cutting-edge stuff. It's a statistical downscale method. Keep that in mind, some of the weaknesses that I mentioned earlier about statistical downscaling. It provides both the baseline period, what's happened in the past since 1950 through about 2005. That's considered our baseline period. And then it gives us future period, future free-run models out to 2100. So it meets the time extent that we need from now out into the end of the century. It covers 20 global climate models, so it allows us to capture the range of different possible solutions for future climate. It allows us to build on the different strengths and weaknesses of all the individual global climate models. These are the same global climate models that are, or at least a subset of which are used in the IPCC reporting, so there's consistency there with what other international bodies are doing. We're focused on two of those emission scenarios, two of those scenarios that are associated with the changes in the atmosphere, those external forces that I mentioned earlier. One is what we call RCP 4.5, that's relative concentration pathway, basically how much forcing is there going to be in the atmosphere, in this case 4.5 watts per meter squared. And the other one is 8.5. We think of those basically as moderate emissions versus high emissions. And they're fairly similar for the next 20 to 30 years. It's only until mid-century and end of century that they really diverge in their scenarios. We have this output now. It's about 6 terabytes worth of output. And this is an example of some of the output. This is a specific day that we just randomly pulled from 2030, showing the minimum temperature that's predicted from one of the global models, in this case, the Canadian model, the ESM2. Just to give you an idea, in addition to precipitation and minimum maximum temperature, which is available in almost all of the statistically downscaled processes, MACA is unique, the only one that has gone beyond that to also take into account and use data sets from something called the National Land Data Assimilation System. So they've downscaled wind speed, humidity, and incoming radiation. And in particular, the humidity and the incoming radiation were requirements for some of the modeling that's going on, in particular for 3PG. That was something that they needed to have. NARCAP had that taken care of. MACA is the first statistically downscaled product that meets those needs. It gives us daily time steps, not that you would want to look at the data on any given day because it's not a forecast, it's a projection. It also gives the spatial resolution that is useful to us, about 6 kilometers. A lot of the dynamically downscaled data sets are on the order of about 50 kilometers. More recently, we have some data that's down to about 10 kilometers, but doesn't cover the full PINEMAP region and doesn't have all the GCMs that we need. And this is an important thing to notice because, I mean, if you wanted to, you could go through the process of downscale, to a few meters. I mean, it would be ridiculously expensive, but also wouldn't really necessarily gain you any new information. So for the PINEMAP objectives that we're looking at, that's not trying to predict what's happening on any specific stand, but what's happening across maybe a county, across a region, 6 kilometers meets our need. So we can still see what the variations may be over a few counties. That's something that we're interested in PINEMAP as a regional project, without having to get too deep into the weeds where we don't necessarily gain any new information from higher resolution. And that's why we're really excited about it. We're looking at a whole range of climate variables. We've mentioned those, but even from those core primary variables, then you have things like number of days where temperature exceeds 90 degrees Fahrenheit, number of days where temperature gets below 32 degrees Fahrenheit, number of days where rainfall exceeds an inch. All of these different variables that we could look at, seasonal precipitation totals, changes in cloud cover, changes in radiation, all these factors, it's kind of overwhelming. What we're going to do is choose and prioritize in consultation with the modeling folks primarily, but also the extension team. What are the things that we need to focus on? Because there's just too much data for all the PINEMAP researchers to handle otherwise. There's just not enough hours in the day to tackle it all. So it falls on us to really help them digest that and then present the data sets that they can find useful that will be efficient and still keep us on our PINEMAP priority timeline. We're looking at both averages and extremes. We're looking at a variety of time slices. So we don't look at what's going to happen on any given month. That's not meaningful. We have to look at what the change in a few decades is going to be over the past. What are the changes in 30 years? What are the changes in 50 years? What are the changes in 100 years in reference to our baseline period? And all of this output feeds into all of the research themes that are going on, primarily the folks who are doing models. Not just the ecosystem and physiological models, but some of the other market models as well. Data is available now. There's been training. There's a write-up that's already been made available to all of the researchers on how to go and get the data. Heather and I are standing by to pull the data as needed. Where it's a few data points that you're looking for, or a few locations, or some simple data sets, you can go and grab it on your own. If it's more complex, we'll write the scripts to process the data for you. But as I mentioned, it's just too much out there. And I've got an example here. So if you just look at annual average temperature, annual precipitation, and mean extreme minimum temperature, just those 3 variables, we have to look at the multi-model mean and the multi-model and the extremes, so you get the range of what the uncertainty is. We're going to do that for both of the RCP scenarios. We have to do that for all the different time slices. So just for one of those variables, for annual average temperature, that'd be 20 maps to look at. So for every variable that you look at, every threshold you look at, number of days in exceedance, for any of the inputs, you're talking about a massive amount of data. So we really do need to figure out a way to digest this down and focus initially on the priorities that are important for PINEMAP work. Now, this data set is, of course, available for anyone to do any other work. It's made publicly available through us. John Abascalu's made it publicly available, so it's out there for others to do it. We're trying to focus on what are the things that are most important for PINEMAP objectives. So this is an example of how we're not only going to take the data and have it run through the models, but it's going to be directly accessible to folks who are wanting to explore it through the DSS. I'm not going to dwell on this right now. This is an example of what you might see in terms of a display on the computer. We'll do live demonstrations tomorrow, as well as we'll give some more examples here in a little bit later this morning of how you might go in and see, okay, here is extreme minimum temperature frequency. There's a number of days in which temperatures get below, in this case, 20 degrees Fahrenheit during the winter based on this RCP scenario for mid-century. And here's where the example is. And you can go in, you'll be able to digest this data, but see it visually across space, but also go in and maybe click on a county of interest. In this county, I think this is Cass County in Texas, and then look at how those changes may change over the future. So it allows us to go in and visualize what's happening regionally, as well as what may happen over time at a focused region of interest. I wanted to recognize and make sure that everyone knows that Heather is here in spirit alone. She's staring there, connecting to that screen over there. She is really the glue for a lot of this and is the one that's doing a lot of that interaction with you. So if you don't have her contact information, if you haven't had a chance to talk with her, make sure that you take advantage of it. Of course, I'm still here. We also have a new member of the team, Corey Davis, who's helping us do a lot of the DSS development, a lot of the data manipulation. He's a brand new climatologist, but he's been working on this and has done a lot of work in particular with fire risk and climate across the southern U.S. So we have a lot of experts here. I also want to remind you that you have climate extension specialists and state climatologists, most of you in your home state, that if you have local questions, they're there and there to answer the questions. In fact, we've been trying to get them involved in a lot of the extension activities, make sure they're going and participating in the workshops. They're another local resource for you. With that, I hopefully am on time, and we'll turn it back over to Tim.